Good morning, guys. It's 11, so let's get started. I already see that many of our friends and colleagues are still on their way, so they will arrive during the day, hopefully soon, so they can take advantage of this workshop. And my name is Mart Orma. I am Head of Space Technology Department of Tartu Observatory, and I'm happy to introduce you the program of the conference, but most importantly, the program of today. Because as you all know from the program, today is Today is a day when we can develop our skills in nanosatellite design. And it's actually very good that among us are people with very different experiences in space technology, in satellite missions. Some of us have managed satellite missions or big satellites, small satellites. Some of you have never had any contact with nanosatellite technology. And of course, in that kind of situation, the best way to share experience between each other is to do some group working. And that is what is going to happen today. So we start with brief introduction. Actually, the number of us is small enough so we can introduce personally each other. I think this is a good beginning for the program, so you know who everybody is. And then we continue with a brief introduction to system engineering, and that will be conducted by Jan Brox from Aalto University. And after that, we continue with mission design, but Jan will tell you about all what's going to happen then. So, in the afternoon, you all have in your files, you have the program, and you see it there. So at 1 o'clock there is lunch, and lunch is 1.5 hours. And there is of course a reason why it is so long. And the reason is that then people can take advantage of communicating with each other. And maybe you can continue with your group work during the lunch, after lunch, if you like. But most importantly, try to talk to everybody at least 5 minutes with everybody you see in the hall. And in the afternoon, we continue with mission design. And for the closing session of the event, then two guys from SQ team will present the latest results of one case study, SQ1, which is currently in the middle of its most important experiment right now, and you will hear something from them. After that, you will have all lunch here, dinner here at Observatory, and then after dinner we have time to look around here at the institute, see our labs, our ground stations, our telescopes. And who has seen it already, then time for socializing again. And at 9 o'clock, we go back to town. Is there any reason to discuss tomorrow's program here today? Probably not, because you all have it in the folder and you made it here today, so most likely we made it here tomorrow as well. So the same way, like bus leaves from Tartu at some point, you see what's the time in the flight. But now there are two important things to do. First of all, where is Jan Brox? Jan Brox is currently flying from Finland to Estonia. Actually, he has landed already, so he's coming from the airport. He will be here any minute now. But what if we start with brief introduction tour, and then we continue with distributing people into, I'd say, 5 groups. Randomly. And then we are ready for starting with the workshop. So, guys, Let's do now a very brief introduction. That means everybody stands up, says his or her name, and I'm coming from this university, and I'm here for one sentence why you are here. So as you see, it's a workshop. It's not like an academic conference here today. So, and guys in the back row, you can start. So, I'm from there, and I'm here for why?
Hello everyone, I'm from Lithuania, from Vilnius University, and I'm here to say hello for my friends from Estonia.
Thank you very much. So, let's continue in the back row. Yeah.
Hello everyone, my name is Max Weiders. I'm from Vilnius University Village in Latvia. I'm here for
And now you can test the microphone and say it all again into the microphone, so everybody can hear you.
Hello everyone, my name is Max Weiders. I'm from Vilnius University College, Latvia, and I'm here for taking part at this conference.
Okay, that's excellent objective. I hope you have some technical things in mind as well.
My name is Jan Stroš. I'm from Vilnius University College, and I'm here to be proud about this group success.
Thank you very much.
Hello, my name is Jan. I'm from Vilnius University College, and I'm here to participate in this conference and see how you do things in Italy.
Hello, my name is Evita, and I'm coming from Vilnius University College, and I'm here to gain new knowledge about satellites.
Hello, my name is Jesus, and I'm from Turkey, and I'm here to be up to speed or up to date with satellite technologies.
Hello, my name is Aldis. I'm from Vilnius University College. I will show you a couple of presentations.
Hello, my name is Paul. I'm from TSTC, the spin-off company from STU, and I'm here to present this nice company to you.
Hello, my name is Urmas, and I'm from Tartu Observatory.
Hello, I'm Jakub Kapusz. I'm from the Slovak Organization for Space Activities. We are working on the Slovak nano-satellite project with many universities and technological companies in Slovakia. And we are here to learn from the success of this key project.
Hello, my name is Jan Salesiak. I'm from Slovak Organization for Space Activities.
Hello, my name is Andrej Zalotsky. I'm from Slovakia, from University of Žilina. I'm here for learn some new technologies.
Hello, my name is Oskar. I'm from the University of Tartu, and I'm here to learn useful things.
Hello, my name is Pete. I'm from University of Tartu, and I'm here because I want to get smart in space technology.
Hello, I'm Oscar, and I'm from Tartu University, and I'm here because I want to learn more about space technology.
Hello, I'm Teres, and I'm from the University of Tartu, and I'm here because I don't know anything about satellites yet.
Hello, my name is Simo. I'm from Tartu University, and I'm here to acquire new knowledge about nano-satellites.
Hello, my name is Jan. I'm from the University of Life Sciences, and I'm here to general insights on subsystems.
Morning, my name is Sarah, and I'm from the University of Tartu, and I'm here to take advantage of everything the university has to offer.
Thank you. And society.
Hello, I'm Henrik
Henrik, and I'm an SQ team member working on attitude, determination and control, and I will be also presenting today.
Morning, my name is Johan. I'm also from the escalation control team, and as I understood from Mark, I think I will be presenting something tomorrow as well. Hello, I'm Emilius. I'm from Mexico's University College, where I'm an intern in Capital Observatory, and I'm working with the European Student Air Orbiter project, which is also linked to the SQ projects. Hello, my name is Christian. I came here from Berlin Technical University, and I'm here to learn about the regional space technology development programs. Thank you.
Hello, good morning. I'm Riccardo. I'm from University of Padua. I'm a PhD student. I'm here because in Padua we would like to start our own CubeSat mission, our first, so I'm here to learn as much as possible.
Hello everybody, I'm Rimas from Vilnius University, and I came here to share our experience from our CubeSat mission. Like I said, one of course to network with all of you guys and share some good ideas, and of course to hear a success story of SQ.
Morning. My name is Dr. Collins. I'm from Big Technical University. I'm here to talk about composite structures in a future logic system.
Hello, my name is Silver, and I'm from Capital Observatory, and I'm here to witness and to contribute to the everlasting success of nanosatellites.
Hello, I'm Denise Inema. I'm working here in the Observatory of Astronomer, but I'm also a member of the SCT, so I'm listening to other external myself.
Thank you. And then there are a couple of guys who should be introduced before we move on.
Good morning, I'm Riho. I'm from Tartu Observatory, and I'm to discuss CubeSats.
So Riho is our head of space technology labs, and later today he will show you around in our lab facilities. And Vilja.
Okay, my name is Vilja. I work here as here at Tartu Observatory as lead engineer. So I'm also a member of the SQ team, and later you will see also our ground stations. So I'm a little bit responsible for those two.
Thank you.
Hello, I'm a supporting member of the SQ. I will help you as much as needed today, and then a couple of candidates. Thank you.
And he has done a great job on the CHS of SQ1. But some new people here. Pekka.
Okay, so I'm Pekka Young, and I'm from Finnish Meteorological Institute. I'm a member of the ESA, which is testing on SQ1.
And you will hear all about it tomorrow morning. Mario?
My name is Mario. I come from the state, from the University of Madrid. I'm taking a summer student in the school.
Thank you. And Erik.
I'm Erik. I'm SQ1 operator, and I'm here to discuss secret mission status and plans with some of the guys.
Okay, and now I think we are ready to one more question. Yes?
I'm Kari, I'm from TSTC, Sweden. Now we have a startup company here in Tartu, and I'm a member of the SQ team.
Thank you. And now I will hand it over to Jan from Aalto University, who will continue. I think you have your own microphones, or you can have this if you like. So we are all yours.
Okay, good morning everybody. So it is going to be a bit hectic, but never mind. My name is Jan Brax. I work as an assistant professor in Aalto University in Helsinki, or in Finland, working also with some CubeSat projects. You're going to hear about CubeSat projects if you're staying in the conference here. But the idea of today was to make a workshop. And make a workshop about nanosatellites. And I was thinking about this workshop. We actually have plenty of time. And we have also plenty of people. And I was thinking that the best way to learn about nanosatellites is to design one. So I propose that we are going to have a sort of competition about nanosatellite designs, and by 4:30 we're going to have 3 or 4 or 5 nanosatellite proposals, real good proposals. So, what do you think? Are you prepared for this type of challenge? Who is not prepared? Okay, you guys are high in the jury. Who is prepared? So it's designed for first timers. So I will tell you how to do and what to do. Who has been designing before a nanosatellite? Who has not even heard very much what this CubeSat actually is? Is there anybody who has not very familiar with space technology? I feel like a bit like in Finland. People are not talking to me.
Jan, there is a very nice way to deal with this situation. So it's like always. Yes, no questions. Are you ready to do it? Yes, hands up. No, hands up. And who doesn't raise the hand, I will come with, where is the microphone? You will meet this microphone in front of your face in 10 seconds if you don't raise your hand. So who is ready to participate actively in this workshop?
Good.
Who is not ready? Did you notice any of your neighbors not raising hands? That was one. Yes, 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 yes. So, you have some different opinion.
My interests are connected to satellite communication systems.
Excellent. And that means you almost have an expert in a team. They will have the best satellite communication experience in their team. So, Jan.
We broke the system.
Okay, yeah. Yes, here is the expert. Help you. But Jan, back to you.
Okay. Okay, so first of all, what we're going to do is, today's schedule is following. First we will wait a bit when this thing will be fixed, and I will get back to my slides. And today I have 3 short lectures. First, I will tell you, by the way, räägin kodakeelse keeles, kellel on mingisugused barjääre, no problem. So I'm going to have 3 lectures. One about mission design for spacecrafts. So, very general, how spacecrafts are usually designed in the big world, and what kind of things you have to consider. Then we have a very short, maybe a bit longer lecture about CubeSat. What is CubeSat? Just hopping through because there is a lot of people who are very familiar with CubeSats. And then we have the first challenge. And after the launch, we have the first review. So review is something which is actually integral part of any kind of space project. So we try to have the first review after launch. After the review, we're going to have also one more lecture on system design. How we do the system design, and then there will be only work. At 4 o'clock, we're going to start the presentations, and by this time, all the teams have designed one poster about Q6 mission with all necessary parts which are typical for a space mission, which I'm going to introduce very shortly. So I think we're going to make 4 teams, and first let's make the teams, and maybe we call the teams according to colors. For example, blue team, red team, yellow team, green team, and we'll start from here. So tell a number from 1 to 4. I mean, you start from 1, we go to 4, and those guys who are staying in jury, you're going to have this day as well, and you are staying in jury, then you don't say a number. So
1, 2, 3, 4, 0, 1, 2, 3, 4, 1, 2, 3, 4.
So your one. Okay, so we have teams. So these teams are at the moment according to the number. So all the ones belong to the first team, number 1, all the 2s, I participate. Number 3. And your number is 2. Okay, brilliant. So I'm going through the first slide set, and then let's see with your team. Is this okay with you? Alright. Actually, it might be better to stay here, otherwise I'm stepping on this. So you didn't have very good system design here. Wait a moment. Alright, so I'm going to tell you a bit about mission design and space project. What is mission design and what is space project? And so this is the dream. This is beautiful. You are on the surface of other planet and you are prepared to work for this dream. But it takes quite a bit of work and quite a bit of organization actually to get there. So let's go through the typical elements of a space project. So a space mission has the following elements. First of all, you need to have a launcher. You need to have a launcher in order to get into space or to do the orbit. And this is the only way actually to access space. And in order to make any kind of space technology, you need to be in space. The ride is quite rough. There is heavy vibrations, acoustic noise, pressure changes, temperature changes. It's a rough ride to space. Then you have an orbit, which is an integral part of your space mission. If you need to carry out some kind of measurements, you need to be on the right orbit. And you cannot be wherever you want. You are operating in the private fields and you have only predetermined ways where to be and how to be. So you have to very exactly design your orbit according to your needs of your science objective. Then you have, of course, spacecraft, which is carrying your payload to the space, and then you have your science. You have normally an entire big team of scientists who are working with your mission and actually defining what they want to measure, when they want to measure, how they want to measure. Additionally to that, you have entire ground segments. You need to have a ground station with satellite links. You need to have a mission operation. You need to have a data center where you actually store your data, which is downloaded. And all these elements are actually a part of practically every satellite mission. Even users, you have still all the same elements. A question to newcomers: what part of this is actually most important part of your mission? Any opinions? I even allow people who have been building users saying what is the most important part here. Payload. Payload, exactly. So, 2 points. Payload is the most important part of your mission.
Objection.
Okay.
Subject.
Yes. Without the subject, you can have mission, but yes. Sort of agree, but payload is something that actually makes your mission happen. So even subject can have several different kind of solutions, and you can study one subject with telescopes or some other measurement means, but your payload is actually why you build your spacecraft. This is the reason. So how to design this kind of mission? And science comes first. So you have some sort of...
Just a comment, there are also other spacecraft, not all are scientific. So.
Yeah, definitely. Now we are talking about scientific mission, but anyhow, let's say mission comes first. You have a reason to build this spacecraft, and from this science objective, or the objective of your mission, might be commercial objective, you start to design your payload, which is defining your spacecraft design, and also defining partly your ground segment design, and propulsion of launchers, and everything is very much interconnected. So, in order to make a space mission, you need to have, first of all, you need to have somebody who is designing this mission, who wants to make a space mission. So there should be a will, and the level should be also skill. So what is the most important element now also missing from this slide?
Funds.
Exactly, money. You need to have funds. So you have to have permission to carry on with your work, and somebody has to pay your rent while you are working on a satellite mission. So typical space project is designed in this way. First of all, what we need to have is you need to have your science objectives. First of all, you agree why are you building this mission. Is this science relevant or mission relevant in a business sense, or it might be even space missions are also built just to show to other nations that we are so cool that we can do space mission. Anyhow, you need to have an objective, and this objective is actually driving the whole mission. First of all, you agree on your objective, and then you drive from this objective your mission requirements. We're coming back to this what is mission requirements. And actually all the missions, including user missions, should be started from science objectives and then derivation of requirements. Derivation of requirements is actually the critical part of the space mission, not really well addressed in user missions, but the more you work with your requirements, the easier is your life after with your mission. So if you get your science objective and mission requirements, you start to study feasibility. Is it actually possible to do it? Is there technologies, is there solutions, is there launchers which actually carry this technology and make this measurement or requirements fulfillment possible? When feasibility is studied and there are identified technologies which should be on board of the satellite, how your measurements will be done, you start with design. Design is actually the major part of your space mission, or let's say not the mission, but preparation for the mission before it, and actually can take almost as long as the whole mission. So if you have a 10-year mission, you might easily also design a spacecraft for 10 years. If you have a CubeSat mission, you have 2 years mission, let's say, 3 years missions, most probably you are also designing and building your spacecraft at least a couple of years. So they are sort of comparable. Designing and building. So all this designing and building is actually going hand in hand. Because so far, most of the spacecrafts have been built as a tailored spacecraft. So all the spacecrafts so far mostly are built and designed for a certain application, for a certain science, for a certain launcher, for a certain country, and so on and so on. And that's why it's so expensive, that you do every single time everything from the beginning, from scratch, sort of. So you can imagine how expensive would be your phone if you would have like a tailor-made phone. Every single one would have like a different phone. Then you need to make some testing. And this is also a part of a space mission which takes a lot of time, because space mission is different than, for example, a software project where you can put like half-ready products to masses and they test it somehow and you will get it back and make improvements. If you launch your satellite, you probably are not able to make any improvements anymore. There has been a couple of occasions, for example, Hubble Space Telescope was repaired a couple of times after it launched, but in most cases you cannot do it, so you have to test. However, the problem with testing is that you cannot actually test it in the proper environment. You cannot test it beforehand in space, most probably. So this is another problem. So you have to invent a series of different kinds of tests how to approach this problem that you cannot test it in a real environment, and you just take one by one. First, you try to test for vacuum, then you try to test for thermal, then you might even do some tests with low gravity or floating devices or something. You need to be very resourceful and inventive. Then you have launch, and then your satellite is actually put into the operation orbit or operation environment, and then it starts to operate, and then you carry out your experiment. And after the experiment, actually, there is also a long life of your scientific data, which is going to be published, analyzed, maybe years and years and years. So, typical missions, for example, ESA missions, are divided into several phases of studies, and the first study you make is a phase 0 study in ESA mission. And this phase 0 study, first of all, you make analysis of mission objectives. So this is the first thing what you start to do. You are naming down why you need to do this mission, why it's so incredible to have this mission, why do you need this data, what can we learn from this mission, and you try to formulate very accurately the objectives of your mission. Why do you want to do this mission, what it is giving? Then you start to analyze the constraints, because there is also a lot of constraints what you can do and what you can't do. So only certain size things fit into your rocket, only certain amount of kilograms can be brought to a certain orbit, and so on and so forth. Then, if you are ready with analysis of mission constraints as well, so you know that this is something is possible to do, maybe not everything, but certainly something is possible, there is technology for it, there is a need for this measurement, for this science, so there is a market for this kind of service, what you're going to provide from space. Then you start to define your requirements. So you start to define what I need to do exactly to get this thing done. And now you're going down the numbers. So you say, like, I need a repetition cycle 12 days. I need to have this data every 12 days. Otherwise my business case is ruined, for example. And this 12 days, it has all the number, it is quantitative, and it has unit, and you can verify it. This is a very important property of a requirement. That you have a requirement, and you can verify. Can you reach this requirement or not? When you also get down with your requirements done, then you go to the mission architecture, then you go to define your payloads, and starting to analyze the environment, and starting to design the whole spacecraft. And of course, all these phases are sort of iterative phases. Even if you're setting up your mission objectives, you already should have a faint idea what is possible technically and what is not. Because, there was in the United States a mission objective to build a Death Star. Valid objective, but not possible to actually achieve. But of course, if you have good objectives, it also turns into a good mission. So, according to this study, you will get the physical mission profile. You get the feasibility study result, which actually shows you roughly where you are going, how much time it takes to actually make the mission with this technology you have, how long you have to develop some technology, and how much it would cost to get this kind of data down to earth, to make some sort of science, for example, or make a commercial service. And after you have been stating this, then you start to evaluate between different feasibility studies. So only very small fraction of feasibility studies are actually leading into a mission. Most of feasibility studies are just made because let's find out, can we do it? Yes, we sort of can, but it's really expensive. Or we can, but it will take 30 years. So most probably drop the case. Most important in your space mission design is to actually back up your objective. You should have a good objective, and you should be very confident that this is really important to do. So you need to justify this to funding agencies, either then national funding agencies or a big space corporation or European Space Agency or whatever. So how do you start typically with this kind of process? First you ask why. So define high-level objective, what will drive the whole mission. Why we need to do this. So you need to be able to give to your funding agency a reason why we need to do this space mission. Why is it so important? Otherwise, they are not giving you money. After you have a very good idea why you need to do it, then you start to specify what you actually need to do. And this is the part where the requirements come in. So you define your requirements numerically as accurately as possible. All the requirements should have some kind of verification method that you are listing down all what you need to do in order to make this science happen. And after you have actually nailed down your requirements, you start to see the engineering work. How we can do it. Most probably there is actually several ways. There might be several ways to make your mission happen. It might be even that actually for this kind of requirements, you can do it with a radio telescope, or maybe an optical telescope, or somehow on the ground. So you don't even always need a space mission. So that's why it is important to list down very accurately all your requirements with quantitative numbers to actually justify your space mission. Because I'm a space enthusiast, most probably as you as well, and I think that it's just cool to make satellites. I mean, it's just awesome. But in order to get actually money and do something reasonable for science, you should justify all these expenses and be really sure that this result cannot be achieved in any ways, in any different ways than a space mission. And of course, rest is engineering work. A lot of engineering to find out how to actually do it. So just a couple of images about missions. So let's talk about requirements. So requirements are these numerical values which are coming when you design your mission. You have your objective already, you know what to do, what you want to do, and why it's so important. Then you need to specify and list down what exactly you need to achieve to get this mission done. And requirements are very important because of several things. First of all, the requirements is the communication. The first communication where you start to communicate as a scientist with numbers and units. You start to communicate what needs to be done. Magnetospheric fluctuations need to be measured with this kind of accuracy. These requirements, then, when they are listed, help you to make decisions. Because the whole engineering process, which is coming afterwards, is actually a series of decisions. You all the time you're making decisions based on something. And if you don't have your requirements, you don't have any basics how to make the decisions. Requirements are driving all your decisions. And requirements also keep your focus on mission goal. So you know that you have to write your requirements for objectives. If I will fulfill all these requirements, I get to my objective. I may get it done. And there might be requirements is the best tool for evaluate between or design between different solutions, which is actually better. You just go back to numbers and see what is better for your requirements. This is also better for your goal. Requirements also help to resolve the conflicts. So you keep numbers like numbers, and you go back to your numbers and say, okay, this number just very simply says like you have to do like this. They help you to find the optimal solution for your goals, and if the requirements are really well made, they even might give you already specifications for lower level engineering. Well-made requirements even might be used as a filter code for your software engineers. So requirements is actually the most important part in designing any kind of space mission. So good requirements are hierarchical. So, for example, you need to specify that we need to make this measurement from 700 kilometers circular orbit. This is a requirement. We need to be there to make, for example, electron flux measurements in 700 kilometers. Easy. But this requirement gives you a whole series of implications. So you need to get there first. You need to get to 700 kilometers. So you have only certain range of rockets which provide you this service. You can call this. There is a certain environment in 700 kilometers. Your satellite has to survive all this environment. There also there might be, for example, mission duration requirement. How long do you need to measure something? It gives you also a requirement for electronics. my electronics has to survive the 700 kilometers for 2.5 years. So this is a requirement. And all these kinds of requirements, which are specified by numbers, are driving your whole mission. The key feature of every single requirement is that every requirement should be possible to verify. If it's not possible to verify, am I actually fulfilling the requirement? It's not the requirement. Requirements have numbers, requirements have units, or they specify something in a way that either through the inspection, measurement, test, or something, you can verify that this requirement is met. So these are the basic properties of requirements. So, for example, a couple of requirements about the first requirement. The spectrometer should measure as many spectral lines as possible. Good or bad requirement? Anybody has an opinion? Bad, definitely. This is bad requirement because it doesn't specify how many spectral lines you need to measure. It doesn't specify in what range of spectrum we have to measure. It doesn't specify how wide lines we need to measure. It doesn't specify almost anything. So whatever we design, we can really design something in design for this requirement. It fulfills the requirement, but it's something really different than we were actually expecting. The next requirement. The mass of the payload shall be 420 grams, plus minus 10 grams. Good or bad requirement? I think it's much better, because it specifies the number, and it specifies also the unit, and it's actually also indicating the verification method. So you just go and measure. And you also know that you have to measure it quite accurately. Not really, but you can also draw some conclusions from these numbers here for accuracy. Very often, if you start to work with your spacecraft, this is actually a famous animal from Austria and Switzerland. It is called Wollmilchsau. When you have conflicting requirements, so you might have all the nice things in your satellite. They might be a bit conflicting. For example, this animal here should be like giving you wool, milk, eggs, and meat, and in some places it also should sing nicely. So these requirements in real life are contradicting. They are not. You cannot fulfill them all. So if you have contradiction in your requirements, you should go back to your science objectives to see what you really need to do, and maybe to use some de-scoping. That means leaving out some objectives to identify what is the most important there. This satellite, anybody recognize what kind of satellite it is? This satellite was almost the Wollmilchsau. This is Envisat. It had 10 payloads, really complicated satellite, but it worked. It was actually possible, but it took like 2 billion to build, and 165 million only to launch, and probably half of the money was spent on bureaucracy and testing, because it was so complicated. And that's why nowadays, what we're trying to do is build smaller satellites, smaller instruments, to avoid this kind of contradicting requirements which are driving your mission so complicated that it drives the cost very high. So the typical tool for a space project, when you need to resolve your contradicting requirements, or just design. As I said, the whole design process is a series of decisions. So in order to make decisions, space engineers typically use trade-offs. We are using trade-offs like in every decision we are making in real life anyhow, all the time. However, you can formalize this process and make a formal decision-making tool, which is called then trade-off table, and you can first decide what are the good and bad points and what is the most important thing for you. And then you just list different solutions and give them points or marks. And after this, filling up the table, the right solution will stick out, hopefully. Or there might be also actually a couple of good solutions even. But this is the most useful tool for a space engineer when you need to make decisions. You make trade-off between two decisions, and it's better to actually make this trade-off with a documented matrices so that you keep these decisions for later use. So very often what you need to do in a space project to come back to your previous decisions and see like, yes, we have to make it smaller, but why is it so big anyhow? Why can't we make it smaller? And then you go back to the decision and see like, okay, there was a certain reason. For example, heat capacity or something was not possible to achieve without this certain size. So that means we have to go back. If you don't keep your track record on these kind of decisions, you say like, okay, this part is so big anyhow, so let's cut it smaller, make another design here, and afterwards you come back, oh crap. We made it smaller, but it seems like we had actually a good reason for keeping it bigger. So that's why you should also keep track on your decisions and your trade-off tables, and you should keep and document your trade-offs during the mission. So this is a project type of process for making objectives and requirements. And this is actually derived in several levels. First of all, you have a sort of scientific theme for your mission. And a scientific theme might be really, really simple. Like, let's go and measure Venus topography. One sentence, one liner. And from this theme, you actually start to work with your real scientific objectives. How often you have to measure, how accurately you have to measure. And then you go to your scientific requirements. And then you go from scientific requirements to observation requirements. So that means you are starting to specify your instruments, how accurate they have to be. And then you go system requirements. What kind of system you need to have to get this accuracy and so on. So this is a bit too complicated for a CubeSat mission, but I'm just showing you how this is done in a ESA project. So this is a smaller mission, and nowadays these missions starts to be more like this MOSS mission. MOSS mission is a European Space Agency Earth Explorer mission, and this spacecraft carries only a single payload. It is all designed for a single payload, for a single measurement, and it does one thing, and it does it really well. And it was much faster mission, much faster building, and a much cheaper mission with a much cheaper rocket, for example, than ENVISAT. So, mission elements, as it was already in the first slide, so you have one of the most important elements is your payload. This is the important element of your mission. What kind of payload you want to bring to orbit, and what is the science, what you do with it. So, the payload is the driver, and actually the whole satellite is built for this payload. So the satellite is giving energy for the payload, it's giving downlink for the payload, it's giving maybe attitude control for the payload, and it gives the thermal environment for the payload. So the whole mission is driven by the payload. Then of course there is orbit, and if you need to be in space, you have to specify where you need to be. And this is specified by your orbit. You have to work with your orbit. Not everything is possible, so your orbit, you are orbiting around the mass center of Earth according to the Newton and Kepler's laws, and you cannot really change it very easily. So you have to first calculate very carefully where you need to be, what are your requirements for ground resolution, for revisit times, and so on. And it has a lot of implications. First of all, the launcher. How can you get to this orbit? Maybe you want to go to the Mars orbit. Maybe you want to go to the Moon orbit. all these different orbits need different amount of energy, which is not possible to achieve with all the rockets. So you're already selecting the rocket for you. If you're selecting the rocket, you need to check, is there launch opportunities for this rocket? How expensive it is? What kind of radiation environment you have around them? Because in different orbits, you have different environments around you. And you have to design your satellite according to this orbit, according to this environment where you are. Also power budget. For example, if you're going to an orbit around Jupiter, your solar constant is totally different than going around Mercury. So it also defines your thermal solutions, power budgets, and everything. So orbit defines also your mission very much. So this is a picture of Van Allen belts. So it depends where you go. It depends then how much you see these high radiation areas, highly fast electrons and protons around Earth in your spacecraft. Launcher is also something which defines quite a bit of your space mission, because a big mission is normally actually designed for a single launcher in mind. Sometimes, of course, it's also possible to change your launcher afterwards, but there is only a certain area, certain volume available in the launcher. And in every launcher, it's a bit different. And there is a certain fairing in every launcher. And that's why you have to design your payload or your satellite. In terms of a launch mission, your entire satellite is called payload. It has to be designed keeping in mind a certain payload or certain launcher. Additionally, for these limitations in size and mass, you have also the certain environment. Different rockets have different vibration environments during the launch. So it depends totally, are you going with a steam rocket or are you going with Ariane 5? If you go with steam rockets, your vibration environment is 2-3 times worse than with Ariane 5. So you have to keep in mind that also this is actually defining your mission. If you go into ISS with a small experiment, it needs not to be so heavily designed for vibration, but it might be very, very high standards for actually reliability and safety. And then mission operation and ground segment. So people often start to design a satellite not thinking how much actually the operation costs. As I said, the design and building of the satellite takes almost the same time as actually operating the satellite. And often it is that operating the satellite might be almost as expensive as actually building the satellite. So because it extends over so long time, you need to take into account first what is your mission duration, how long you want to operate this satellite, how much data you need to process, what kind of antennas you have, what kind of data links you have, what is your mission requirements, can you get maybe less data down? Data redistribution, do you need an entire network, do you need from Russia, but you cannot just transport so big stuff from France to Russia easily. And you have to take it into account. And storage also. Some of the scientific instruments might be designed for use in a vacuum or in a radiation environment, and you store it in a different, you might store it in an atmosphere, maybe even a humid place, and that will spoil your entire measurement, maybe. So you have to take this also into account. How long time you have to wait before your satellite is getting launched, and where and how you have to store it. It might be actually quite expensive to store your satellite for extra 3 years in a clean room under very regulated humidity conditions. Descoping. So something when you designing your satellite, you should take into account also is descoping. And descoping means that you should identify the parts of the mission which are absolutely crucial, without what you cannot do your mission. But they might be also nice to have missions, because we are not so often going to Mars or Venus orbit, and maybe even Moon orbit, and it might be like there is a small instrument we can accommodate on this flight, and just nice to have extra science with a small instrument. However, you start to apply for money for your mission. And you said, okay, 2 billion, too big. 1.5 we can manage. And then you have to descope your mission. You have to identify what is the most important one, what are the most important requirements and objectives, and descope the other parts. So it might be a nice car to have like this, but maybe it's more expensive and you just have to go with a normal one. This kind of decisions you have to make all the time. So either you have something simple and reliable, or you have something fancy with all the different parts, bells and whistles, different sensors and things, but it's not so reliable anymore, and maybe it does not suit so well to any of those tasks. So this is, when you are designing a mission, this is something to keep in mind, that do you go for absolutely 100% reliability for your mission goal, or would you like to fiddle with different side projects, different other projects and additional parts there, and actually you can make your mission like this as well. Because it's so rare to go to Mars or some other places, on Mars we have this kind of instruments. Instruments which are having a lot of stuff, measuring a lot of stuff, and this is actually like if you are a really tight place on the deserted island by yourself with one tool only, this tool is actually better because you can do a lot of things and you actually can get more information from Mars with this kind of tool than this kind of tool. But for example, if you are designing a commercial mission to a geostationary orbit, maybe it's better to go with this. This is reliable, delivers your business, and that's all. So programmatics. This is the part which is called programmatics in space terms, and this involves cost, risk, and schedule. So first of all, a schedule of a space project, according to ESA definition, is divided into those phases, phase A, B, C, D, E, F phase. And phase 0 is something what I already referred to, and this is the mission analysis or the phase 0 study, feasibility, or the actually mission analysis study. Then you have a feasibility study, and what we want to do today is have actually phase A and 0 together in a small study where we actually build a CubeSat. Phase B, you start to define your system. Phase C, you make the real blueprints for your satellite. Everything is already tested, fitting together, working together. And then you start the production and qualification. So you make your satellite and start to qualify that it actually can work in this space environment. And then phase E, after launch, is utilization. So you use your satellite. And not to be forgotten, this phase F, disposal, is more and more important nowadays as well. So especially if we are launching small and cheap CubeSats and other satellites, we need to take also into account how to get rid of those satellites in space, because this is a very finite resource, the space orbit. So I'm so glad that we are actually doing a lot of deorbiting studies already. So this phases, if you start to build your mission, you start to maybe work with this kind of Gantt charts, where you actually make different phases on one paper. And as you see here, there's arrows in between two phases, and these are called reviews. So in typical space project, you have a lot of milestones which are called reviews. So reviews are really good idea. Reviews are ending your certain part of the project or project phase, and you go into a review. It concludes your documentation, fixes your design, and it gives the whole design and the whole concept for evaluation to a review board. So review board is also often introduced from outside, so you have unbiased opinions there, and not all the CubeSat projects are using reviews, but I think it's really good idea to even have a review in a CubeSat project from every now and then. Most probably you don't have to have so many reviews like you have in a big space project, where you have, after every major phase, you have a review, and either after the review you can continue with the next phase, or you turn back to the previous phase, you have to do some error correction and go back to the review and then proceed to the next phase. But review is something really important. This is the calendar which is actually making the pace of the space project. Cost. Cost is really tricky to estimate, and this is absolutely unbelievable that there are people in the world who actually can estimate the cost, just saying like, okay, you have this kind of project, you want to build it in 2 years, I think it would be 500,000. And it comes from experience, but there is already also a sort of formalized approaches how to analyze the cost of the spacecraft according to the orbit, launcher mass, and time. And yes, this is what ESA does, because you have so big missions and you know you need to specify your amount of money what's available. Risk analysis, also very important part of a space mission. So if you start to make decisions, you start to make your design, and you see like, okay, not everything is here yet, we have to design it first, you have to analyze how risky it is to start the design, or what happens if. So you have to prepare yourself also to sort of alternative scenarios. What happens if, I don't know, Hungarians are not delivering the radio? What are we going to do? Because it's outsourced and their company is very small. Maybe it's bankrupt. So you have to go through all your risks also, and for risk analysis in space projects, this kind of risk tables are used. And if you go for a mission, then if you want to get this mission proposal accepted, never you should have anywhere high or very high. Red color is prohibited. Otherwise, you are basically not getting, in very rare cases, you are getting your thing or your mission through. But you should be in a medium or low risk area in most of your risk analysis. So other things to consider, product assurance and quality assurance. So because you're working with a complex systems, you need to introduce some kind of quality process that involves also, for example, documentation. And documentation is in any kind of engineering project, especially in a big project, really important. So the bigger project you have, the more important the documentation is. And documentation is not important for documenting things. things or following ESA rules or NASA rules. Documentation is the main tool for communication in your project. So if you have 125 engineers working on your system, you have no chance to actually communicate orally with them or having coffee break from time to time. Coffee breaks are actually really important for communication exchange. But if you don't have these 125 people coffee breaks every Friday, you have documentation. So your documentation is actually carrying all the information from one side of the project to another side of the project. So you have to be sure that your documentation is up to date, you have version control, there's naming conventions and indexing, and you need to take care that this right information finds right people at right time, and they are not getting old, outdated information. By the way, documentation doesn't need to be a paper-based documentation or even similar to paper documentation. You can have a rapid development methods where you don't have a paper-based documentation, but maybe you work with just spreadsheets or tables of numbers, which are always electronically up to date. So there's different approaches, but anyhow, some kind of documentation is really needed if you have any bigger project. Maybe if with 5 guys to make a CubeSat, you can make it without the documentation, actually. It's possible. But any bigger project, documentation is important. So technology readiness levels is something, if you go to the bigger projects and ESA projects, this is something they start to talk right away. Is there a technology readiness for your subsystem? So technology readiness level means that you have a standardized, this is actually coming from ISO standard as well nowadays. Do you have readiness to actually do something? And this affects your price and development time and so on and so on. And if you just have a basic principle observed and reported that something can be measured through this phenomena, then technology readiness level is 1. And technology readiness level is 9 if you have it already operating on one satellite, measuring the thing and delivering the data. And you want to use exactly the same instrument on a different satellite, but measuring the same thing, just more frequently. So this is a technology readiness level 9 for this instrument then. And all these things between, like breadboard versions and everything, have their own technology readiness levels. This technology readiness level is a hard currency for big space agencies or big space missions. So if you start to negotiate about the project with ESA, and for example, you have flown something with your CubeSat, and you say like, okay, we can do something like this, and they said, yeah, but this is a school project, and if you can show that we actually have been flying this in space, this is convincing, because it has very high technology readiness level then. You can prove that it works, and also space people take CubeSat project seriously, and this is one of the most important areas where big space corporations, big space industry looks to CubeSats, that they can make proof of concept flights, technology demonstration flights, and get the technology readiness level high with a very cheap and small flight. Then you have to take into account that this testing for space project takes a lot of time. So even if you think that, okay, yes, let's build it, most of your time in a student project, in CubeSat project, you spend on building and designing, but you should also spend a lot of time on testing, because this is actually what gives you the guarantee that all these things are working. I don't have a slide, but another thing what you should do is software. So software is also something which takes a lot of time, and normally somehow we are wired in a way that if we have the physical object, it's all right, then it's done. But actually it's halfway, because you need to also make the software. And as you see, it's a vast field of technology with a sort of peculiar on traditions and
sort of peculiar practices which you don't know all, then don't be shy to use standards. So there is several organizations who are actually standardizing all these approaches what are used in space industry. And the biggest one in Europe is European Corporation for Space Standardization, ECSS, and they have standard for almost anything. So this is the tree of standards. Like you have standards for product assurance, you have standards for engineering, you have standards for project management. These are actually manuals. So if you don't know how to do something, go to ECSS and see how these space guys are doing these things. And maybe it's not applicable like this. It's too expensive, too time-consuming, and so on for a CubeSat project. But at least you will find out how people have been doing it. And these standards have been developed for necessity. So they are not just for bureaucracy or something. You really find a standard how to glue with the silicon or what kind of diodes you should have. Everything is somehow standardized. If you don't have standard, the problem is that then you have to verify or qualify yourself that it actually lasts in your space mission and actually can withstand the environment. If it's already standardized, that means that there has been like tens, maybe hundreds of people already working with it and getting this thing somehow functional. Okay, about today, I was thinking that now we have teams. We have 1, 2, 3, and 4 teams. We can assign now colors if we want. We can also operate with numbers. And I propose that we are going to do a mission. The schedule will be following. First, this lecture here, Space Mission Design. What is space mission and how to design it. And then we have a small break and going to give a small lecture about CubeSat. And then you start to work with your mission idea. So let's try to develop a CubeSat mission idea in a similar way like it is done in a big space projects. When we're going to have a lunch, and after lunch we're going to have 4 reviews differently. So you are all competing with each other, so that means we're going to have a secret reviews for each team and checking do they have a viable idea for a mission. And after that, I'm going to give you a small lecture about elements of system engineering. So how you build a system, and then you make a mission design, and the result of your work is a poster, like this. And as you see, this is like all structured out now, how it should be done, how it normally flows, and all these parts you should be somehow presented on your poster. So you start with the mission objective, you go to the mission requirements, and from mission requirements you derive your payload, your orbit, your launcher, your ground segment, and ending up with a mission description. And from payload, you also go to your spacecraft design. Now you have very heavy restrictions because you are working with CubeSat. Your size is very limited. You cannot go bigger. But then from spacecraft design, you make your product tree, what kind of parts or functional parts your satellite needs. You can end up with a drawing of your spacecraft, and you can also make telemetry budget, power budget, and mass budget, the most important tool of any system engineer. And you can also assess risk, cost, and schedule a bit. So after these things are written in a big paper, on a big paper, you have a mission. So this is how missions are often done. And we have evaluation board who is going through your final presentations. We're going to have 4 times 4 presentations. All the presentations are at the same time, so we're going to have 4 posters, and we are going around with 4 groups, so that at least 4 people from the team are going to present their poster to all the rest of the audience, including the jury who is participating in this round, and we're going to have a winner. So that's it. Any questions? Anything? By the way, anybody has a computer? Who has computers? Brilliant, brilliant, brilliant. We're going to have 5 minutes break, and we will team up with teams, and you will find a small table or somewhere where you can meet. And I will prepare my next lecture, which I'm going through very quickly. And CubeSat is an interesting beast, because for CubeSats, you can get things commercially online. So in order to design a mission, for example, for mass budget, it's rather easy. You just go to the web shop and see what's available. What are the parameters? Are they meeting my mission objectives? And in this CubeSat-wise, we can actually hammer a mission together like in half an hour if we really like. So don't be afraid, but you're going to need your computers because you have to browse some internet to actually make your mission happen. All right, 5-10 minutes break, and all the teams are going to find places. So, Marttu, you have a place for team number 1.
Yes, let's use this 10 minutes break now to get familiar with your group. So, guys, number 1s, come over here. Number 1s, remember. And each of people who joined our team later, so you can select number at your own choice. Is it 1 or 2 or 3 or 4? And some more experienced guys will join jury. And well, and Jaanis, it's up to you if you would like to join jury or be part of the group. So you decide.
Okay.
So
next
guys, number 1. I will show you your room. I will be guys number 2. Meet there. Guys number 3 there. Guys number 4 there. 4, 3, 2, 1. Group 1, follow me. So guys, I will give this post.
All right. So I hope you found your team, and we have 25 minutes, actually 20 minutes, to just go through very quickly CubeSat. So who knows about, or who doesn't know anything about CubeSat? Good. So we have people who are basically knowing all about CubeSat. Who knows just a little? Okay, this lecture is for you. So CubeSat is a very small nanosatellite standard. And why is we hear about CubeSat? Because the expensive launch of space industry is actually defining the whole industry. So it's the 50 or even more years old technology. We're still using the same rockets, still same chemical propulsion, and it's still unreliable, expensive, and so on and so on. And that's why the whole space business is so expensive that you don't have an opportunity to lose your satellite, and it's so expensive to get into space. So if you can get your satellite to space with much less money, you can start to think in a different way. So this was Envisat launch, 140 million euros. In nowadays money, it's something like 170 millions. And if you compare this price to a small launch price of a CubeSat, you can see the difference. It's like you would have this car out in the sales for like 40 or 30 euros. So this is really changing the view, because we can build a fully fledged functional satellite doing something useful for this small money, the whole scene will change. And this is actually what is happening. So we have a lot of small satellites nowadays launched. So last year in November, Dnepr actually launched like 24 payloads at the same time. If you take into the consideration that there is only around 1,000 functional satellites, and you are launching during 1 year almost 100 more satellites, this is a revolution. So last year it was almost 80 satellites launched, and this is the spring statistics. And another thing which is happening now with our CubeSat is that commercial market is coming to this segment, and commercial enterprises are launching their satellites. So it has been steady from the born of CubeSat standard, And now it starts to boom. It starts really to shoot up. So that's why I believe that you all, if you study hard, you have a future in a future space business. So a lot of countries are building CubeSats. The leader is, of course, the born country of CubeSat, United States, but there is a lot of activity also in Europe and in the rest of the world. So small countries like Estonia are becoming spacefaring nations because they are able to build and launch a CubeSat. And this changes everything because international politics, space is, by the way, like international waters in ocean. So everybody has the right to actually utilize space, use space, study space, make science there. If all the nations would launch like 200 satellites, like, let's say, Chinese people, or 500 satellites, like United States, the whole scene would be a totally different scene because we have to have new regulations, new launch markets, and so on and so on. And everything this is actually emerging at the moment. So CubeSat is a small cubical satellite standard which was designed in Cal Poly and Stanford University in the ends of 90s, 99, something like this. And from 2000, the saga of CubeSat began. So nobody actually was taking this very seriously, but with a very small amount of money, you can build a fully fledged satellite because nowadays the mobile computing technology is so small, the sensors are so small and so miniature that you actually can put all these things into a single satellite. The biggest game changer here is the standard. And this is the CubeSat standard, and those who don't know, this is entire standard almost. So this is as complex as it gets. So this is the whole standard. If you want to make a bigger one, this is another sheet of standard. So this is less than 10 pages of standard for this satellite. And this is the beauty of this standard. So it defines 10 times 10 times 10 centimeter cube, defines the materials and the interface, outer interface to the launcher, and that's it. Nothing else is standardized. So CubeSats looks a bit like this. A small metal cubes, these areas here, the rails, these are actually defined what they should be. Everything else is pretty free. You can put antennas or solar panels, make them out of PCB panels or aluminum panels or titanium panels or whatever you want to do. So these kind of very small satellites with their own solar panels, they have different materials, different missions, and they are typically built in universities. Part of the standard is this box here, and this is called PBOD. It's the original launch deployer for a CubeSat. And this is actually maybe even the most important part of the standard, because nowadays all the launcher companies, they have this box, and this box is safe. The CubeSat, even by students, built by students, the CubeSat fits inside, and it's totally shielded from all the other payloads. So that means you can put like expensive big satellite to your launcher. You still can carry, let's say, like 200 kilos. Why not to sell this excess weight you can carry to the orbit for these CubeSats, if you can deploy them safely? So with this kind of deployer, you can first deploy them safely. It's isolated from other payloads, and it's standard. It's interchangeable. So it doesn't matter. You don't need to book your launch for next 7 years. You can maybe launch next year because there has been somebody booking a flight for the CubeSat, but they are not getting it ready. You can sell the place to somebody else. So this standard has created the launch market. And the launch market is really important because this creates the launches to the space. And as I said, if you want to make space technology, you need to be in space. With this, you can go. So there is already several versions. Last one was American one. This is a German one. This is from Holland. So you have different small companies providing different launch ports or deploy ports for CubeSats. And they are as safe as all the other ports. And all these small companies, they are also selling you launches for your CubeSat. So you can go to the web shop, send an email, and ask, can we have a CubeSat launch somewhere next summer or in 2 years or something? So CubeSats are put into these spring-loaded boxes, attach it to the fairing, and there you go. Spring just pushes off your satellites, and you have a space mission. There is another important standard, which is sort of industry standard, which you should be aware of. The very early CubeSat brought to market a company called CubeSat Kit. So people started to sell a small kit, which is sort of homemade satellite basic kit. And this satellite kit adopted PC104, PCB electronic standard, to be used inside of this box. So these are the satellites, and this is the basic electronic board, which was sort of standardized by this company, Pumpkin. And it looks like this. So because of this company heritage, most of the CubeSat sets look like this nowadays. A stacked configuration, stack-through bus, and sort of modular design where you have all your modules. But make no mistake, this is not part of the CubeSat standard. This is de facto standard, de facto industry standard, so you can go to the web shop and buy a radio according to this standard, or reaction wheels according to this standard, or even camera or something. But this is not the CubeSat standard. CubeSat can be from inside whatever it wants. So because there is this kind of standards which are coming more and more popular, you can create web shops. And there is already, I think there might be even 10 of those web shops. So small companies selling CubeSat stuff. So if there has been a satellite on orbit, you can sell, for example, its radio designs, you can sell its onboard computers, sensors, antennas, and so on and so on. The biggest company in Europe is ISIS, and don't mix it up with another ISIS, which appeared to the map recently. They operate a place called CubeSatShop.com, and they actually sell their different kind of parts, and there is everything you need for a single satellite, from batteries and solar panels to cameras, onboard computers, and antennas. Everything is there. So they go around the world in conferences and selling and promoting their stuff. There is also Blind Space from Scotland, who is also selling CubeSat parts. So most probably for all the CubeSat people, these shops are very known already. And there is also GomSpace, there is CubeSat Kit, there is different companies selling these parts. So launch market. So the same EASYS is actually selling also the launches. What it does, it makes a deal with a launch provider. This is a Vega rocket, which brought 6 CubeSats to orbit. And here you can see these deployers here. And what they do, they take some money and actually make the paperwork for you. It is possible to also buy your own launch from directly communicating with a launcher. But nowadays, even launchers prefer to have this company because they have so long business heritage with them, so they can trust them. However, as you see, the spacecraft amount has been like going rapidly up. There is one important issue with this CubeSat is space debris. These CubeSats or any other satellite, according to the nowadays agreements, international agreements, you should take care of your satellite after, or you are sort of allowed to have 25-year mission, and then after 25 years, you somehow should get rid of your satellite. And this is only possible if you launch your small CubeSat actually to quite low orbits, like 600 and something orbits. Otherwise, it does not come down by natural decay. So this is a small problem, and that's why this kind of deorbiting mechanisms are quite popular study topic. Most probably this guy who has been drawing them, this just like has some kind of data points there, and I don't know. I don't have answer. So there is several options for deorbiting, and for example, S-Cube and ALDO-1 are both trying to utilize and study the electrostatic sail for this purpose. And let's hope we can get some data. At least we get a lot of experience on this technology. And this might be one of the technologies which brings the used satellites down from orbit. So CubeSat typically uses like a module, which is a radio. CubeSat typically uses radio amateur frequencies. And this is another problem. Radio amateur frequencies cannot be used for commercial purposes. So if you want to build a commercial satellite, you have to go with a commercial road, and then that means you have to apply from ITU your frequencies for satellite, and satellite frequency is given by ITU at maximum 7 years. So ITU reserves 7 years' time to give you the frequency. Unfortunately, this is way too long to wait for a CubeSat mission because you want to make your mission in a couple of years. So far, most university missions are using, and even some commercial, sort of half-commercial missions are using radio amateur frequencies. Unfortunately, radio amateurs are getting a bit more and more annoyed all the time about these satellites because they are so many. But yes, you build antennas, you can use also the higher frequencies like S-band, for example. There are already CubeSats using S-band in space. And ground segment, instead of having this kind of big hall of operators, you have maybe one antenna somewhere in an isolated place or on the top of the roof, and your whole radio equipment might be as well fitting into the USB stick. So it might be a software radio solution, which is really small, really mobile. Unfortunately, your CubeSat is still operating with so low power. It's only 1.5 watts of radio power, and that means in order to take this power down, you need actually pointing a tracking antenna, because satellites coming and going over you like 10-15 minutes, and then it's gone, and you have to wait like a couple of hours, 1.5 hours, another 8 minutes, and then you go for coffee for 8 hours, and then you could come back and see your satellite again. So the tracking antenna is a problem. But there are already activities in radio amateur community to bring these satellite stations or ground stations together, make different kind of networks. One was even ESA was funding this project, Genso. Unfortunately, it's still sort of pending and not working. But yes, this is a Korean, I think, art project. So you can make different kind of antenna systems. You see, this is quite original way of making a Yagi antenna, sort of. So you have totally portable, small antenna. But yes, you can have a portable antennas and go around with those. And that's why this CubeSat community has been full of different kind of innovations. This is a Japanese satellite which is blinking in the sky and making a Morse code as it goes over. This is an Italian project where they're trying to print with 3D printer the whole satellite. So you just like download your blueprints and print the satellite, and off you go. There is software radio solutions where you have a single software radio is taking care of GPS, inter-satellite communication, ground communication, everything. So there is projects which are trying to use Arduinos in a CubeSat. There is our project which is trying to put small spectrometers and having actually remote sensing satellites. This is different optical configurations for very small satellites. You can even have multiple satellites flying together. Sensors. You can even have like mass spectrometers nowadays for CubeSats. This is quite amazing, actually. And there is extreme case of TIVAC, actually from the same university where CubeSat standard is coming. The whole CubeSat sort of technology electronics is squeezed to this plate here. So this is the CubeSat. The whole CubeSat is empty, but what they do, they build the whole satellite technology as they would build a laptop computer. They have very small connectors. Everything is integrated. For example, the entire EPS system, power system, is integrated to the boards of your solar panels. So what you can have is entire satellite actually for your payload. You go to the shop, you build this platform or buy this platform, and you have the entire almost 1 liter of volume for your payload. So you can put anything you like in here. So another approach, different kind of phone sets, and this is a strand by Surrey, trying to use existing electronics like phones, where you have most of the stuff which is needed for a satellite already existing. You have gyroscopes, you have magnetometers, cameras, all the radios, central CPU, everything is there. Memory is there, everything is there. So if you could go to the shop and buy for 200 euros entire central processing unit for your satellite, wouldn't be it awesome? It would. This mission actually brought entire CubeSat to orbit and watched with camera, actually, not this camera, different camera, this one, I think. They watched how this, they had a serial connection, of course, to the phone, but they also monitored the screen of the phone. Was nice. So you can also fiddle with new concepts of swarms or constellations. So bringing more and more satellites to the orbit, and these satellites start to form any kind of big mirrors, big antennas, synthetic apertures for radio measurements, and so on and so forth. Biological experiments. You can fit a small satellite with the measurement units and bacteria, which would be quite expensive maybe to do in a bigger satellite. You can do it cheaply with a CubeSat. Yeah, different kind of satellites. Yeah, this is Planet Labs. So Planet Labs, one of the first really successful companies, they started to build CubeSats, and they equipped this CubeSat with an optical camera, which actually is able to measure 5-meter resolution, ground resolution images. And their plan is to actually populate the whole sky with these satellites, around 100 satellites, maybe a bit less. With these satellites, what you can get image coverage around the world in 1 or 2 hours. Now, if you look to the Google Earth, you can see there is satellite images, but they are half a year too old. And this is something peculiar with satellites, because you cannot drive the orbit. It just goes out as it goes. You need a lot of satellites. You actually get the up-to-date data, because the real world doesn't work like a James Bond movie. Then you just like order your satellite, they take picture. If you have 100 satellites, you can do it. So these are the Planet Labs guys, and these are actually their satellites tested and launched from International Space Station. There is different kind of ship detection, eyes applications, different ideas about constellations. Yeah, now we are already going to my backup slides. So, yeah, this is an interesting project. KickSat, you are making one big CubeSat full of very small satellites, which every single one has their own radio and their own measurement unit, and you spread them out from a bigger CubeSat. So you can have, with one launch, like 2,000 satellites, if you really want. This is a military application, but if you can get more satellites to the orbit, it will give you several advantages. First of all, CubeSat is affordable, it's standard, it gives you flexible launches, it's open source, a lot of things are available because it's student projects. All the student graduation works, like diploma works and master thesis, they are public. You can go and download how they have been making these satellites. It's a big community, it's community supported, subsystems are available commercially. There's a lot of education on this field also, because CubeSats are used as education. So if you're trained to build the CubeSat, what do you do after you graduate? Start to build CubeSats. So it has a modular design, although the CubeSat kit standard bus is quite a pain in the neck. It's not the optimal one, but we have to live with it. It's really giving you fast development times, so military organizations can develop CubeSats in a couple of months. It's very suitable for high-risk projects or high-risk ideas because you don't need to put so much money into it. And it gives you a lot of innovative science at the moment. And also fast spin-offs in commercial sense. So CubeSat is really important and interesting platform. It's showing the road to the future. However, it doesn't need to be the CubeSat which is the future. But modularity will last. Standards will last. Community will last. All these important sort of case makers are making these satellites viable also in the future. And also making the opportunity for you to actually participate in space technology and space industry in the future. Okay, this was pretty much what I was planning to say about CubeSats. And now we're going to have lunch. And after the lunch, we're going to have your first review. So I hope that you are coming up already for review a formulated mission idea. Some kind of an idea. We also have some printouts here. So you saw the slide. I was visualizing what kind of poster you're going to have. There is a template. So if you just fill up these parts, you're going to have entire space mission, phase 0, and feasibility study. So, thank you very much. See you after lunch. We're going to have the first review at 2:30. And now Mart takes over and says where we have lunch.